Hello, RDs and RDs to be. Welcome to the RD Exam Ready podcast. I'm Zach Caseberg, your tutor, coach, and guide along the path of passing the RD exam. And my biggest passion is helping RDs and RDs to be just like you to know how to effectively pass the CDR exam. If that sounds like you, then hey, you're in the right place. All of life starts with science. I think we forget this fact that the subjects we learn all the time directly transfers to the cells within our body, into the things that we eat. On the CDR outline, if you look, you'll notice that the very first page begins with food science, specifically about physical and chemical properties of water, fruits, veggies, sugars, flours, grains, and beyond. This section is assessing if you understand the science behind the foods that you eat. Now, you know that food science, you know it a bit, at least from some of the courses that you were always participating in, but most of us aren't always studying food science. Most of us aren't always using these skills, so we can become a bit deficient in this information. Today, I just want to talk about the physical and chemical properties of water and give you the basics that you need to know for the exam. A very simple lesson for a very simple day. Now, grab something to drink, maybe a colorful snack, because you are going to need all that you need to know about water here. We're really going to dive into the waters of physical and chemical properties of water. Okay, I'm going to cut it out with the puns and get serious here because they're going to start to get worse at some point. Let's put method into the madness to learn this subject of water. With each topic we're going to talk about here, I'll be discussing some of the physical properties of it. We'll discuss the physical structure, the molecular structure. Then we'll transfer that into how it actually goes into our food and chemical properties of these different topics. Water is essential for all stages of growth, of life, and of development. It provides all we need for the life functions of assimilating, digesting, absorbing, transporting, metabolizing, and excreting a lot of our byproducts. Water consists of three atoms, one oxygen atom and two hydrogens that are attached. And what you should know about water is its polarity, it's very neutral due to its combination of two positive hydrogen ions and a negative oxygen ion that has a 2 minus charge. So when we have two positives and two negatives, that's what makes it dipolar. This dipolarity is what helps water to stay bound together and gives a lot of those chemical properties that we know. If you'd like to test out a little bit about these chemical properties, think about a glass of water and if you fill it up underneath the faucet. Watch what happens. When you fill it up all the way to the top, the water won't necessarily run over if you stop it. The water will be a little bit higher than that glass. And that is due to the surface tension of water, and its polarity is what contributes to make water so strong and have so many properties. There's two sources of water in food. You have free water and bound water. The free water is that water that is found throughout your food. And what we mean by this is if I take an orange or a peach and I squeeze it really hard, you're going to see water kind of squeeze out of it, right? That is going to be the free water that is within that food. Now, bound water is water that is kind of chemically bound within things. Let's take bread for an example. You use water to bake bread, and water is within bread. But if you squeeze that bread loaf, there's no water coming out of it, right? So that is that bound water, and it cannot be easily removed out of things. It's quite resistant and quite trapped in there. If you really need to get the juice or water out of something, we'd rely on things like fruits, vegetables, or water itself, as it's going to be very dense in free water. The properties of water is that really it gives you an idea of how water is oriented in different states. As a liquid, water is in constant motion with itself. These are bonds that are breaking and bonding, and there's kinetic energy all throughout this process between the water molecules. So they really all do flow together as one when it's in the liquid state. When you freeze water, the orientation of those molecules is going to change. The lower the temperature decreases that kinetic energy between the molecules, and it slows those molecules until they file into this kind of organized rows, as you can picture them, instead of constantly moving. They also expand when this happens. Water will expand when it's frozen. And you see this if you take a mason jar, fill up with water, and freeze it. You'll notice the jar will often break or the metal part of it will expand. And that's because of how that water expands when it's frozen. Now I want you to imagine what happens when you do this with food. Because if I take fruits, vegetables, they all have water within them. And we know freezing definitely changes a bit of the quality of things. So, why does this happen? Well, that water that is still within the fruits and vegetables, when I freeze them, the water expands, right? So, you see this expansion. And so, when it expands, it's probably breaking a lot of those cellular membranes, those plant cell walls. A lot of those are being expanded and broken when they're frozen, thus why your fruits and vegetables may have a bit lower quality whenever they're frozen. So now you know why this actually occurs. Excuse me. Key point here, RD, to be water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. Make sure you know both. Now, conversely, what happens if I boil this water? When water reaches its boiling point, the water isn't getting any hotter. Once it's reached that boiling point, it stops its highest temperature at that point. The boiling point of water will be 212 degrees Fahrenheit or 100 degrees Celsius. In this state of boiling, those water molecules are moving really fast. Lots of energy has been packed into them, and so there's lots of kinetic energy, so much so that they end up escaping and vaporizing and becoming steam in the air. This happens, work with me here. This happens when the vapor pressure of the water equals that of the atmospheric pressure around it. Let's use an example to help us understand this. When I use a pressure cooker, what I'm doing is I'm placing a lot more atmospheric pressure in this small space, right? I'm trapping all the air within this small space. Now, when I'm heating water within there, I'm trapping that pressure, and the water is really getting hot when it does this. So, in a pressure cooker, you can reach upwards of 250 degrees Fahrenheit for the boiling point of your water because of how much pressure it's being placed under. So those water molecules are moving way, way, way more fast because they're under so much extra pressure. In higher altitudes, atmospheric pressure is lower. The air is thinner when I'm at higher altitudes. Less pressure means that those water molecules require less resistance to transition to a gas. Okay. So if I'm on a mountain and I'm boiling water, what I'll see is there's less atmospheric pressure. So my water has less resistance to reach its boiling point. The boiling point of water at higher altitudes will be lower. Your boiling point will be lower at higher altitudes. Maybe something, let's say 200 degrees Fahrenheit, will be your boiling point. The reason this matters for you is because if you're cooking, you're going to know that it's going to take a longer time to cook those foods at that lower boiling point. Because if I'm cooking at 200 degrees instead of 212 degrees, whatever I'm cooking is definitely going to take longer. That's a big mix one that I always struggled with when I was studying. So I hope that made sense of how I can do that. Now, I can manipulate boiling point or freezing point with things like solutes, such as sugar and salt. While boiling, if I decide to add water or sugar, you're going to see the boiling point increase. It starts to require more energy or higher temperatures to get your water, that solvent, to reach that vaporization point because it's got all this solute within it. Candy making, I think, is a good example. If you add a lot of sugar to water, what happens? Well, when you boil that candy and you try to put it on a pot and a hot stove, you're going to heat that candy water mixture or excuse me, that sugar water mixture. And as it reaches 212 degrees, candy gets very hot when it's cooked. So it doesn't stop at 212, it just keeps going up. And that's how the candy ends up being caramelized and cooked and boiling and becomes hard candy, is because you have heated everything to such a high amount. The sugar is what is allowing you to heat that water to such a high temperature at that point. With freezing point, we're actually seeing something different. Addition of a solute like salt or sugar will actually lower your freezing point of water. And we see this in ice cream making because we add sugar or salt in that ice cream process, and it makes the freezing point a little bit lower. So when I'm trying to get my ice cream to form, I'm not seeing so much ice crystals and ice form on it because my freezing point is so much lower. We don't want ice to form very much when we're making ice cream. We want it to stay nice and creamy. So that's why adding those solutes will lower that freezing point and you won't have so much ice form. Okay, now you know your physical properties. Let's get into the chemical. In cooking, we see water used in in most of the moist heat cooking methods. Steam and boiling are great examples of this. This form of cooking is what allows for more consistent cooking throughout the food. For example, if you cook asparagus on a grill, what you're going to see is the asparagus is browned, caramelized a little bit, right? Whereas if I decided to boil it, you're going to see that asparagus is cooked very consistently throughout because it's completely covered in the water or the steam. There's no part of it that's getting more contact with water or steam. Whereas on a grill, you're seeing parts that get very browned and less browned all throughout. Both have desirable factors, right? As a solvent, water is the great universal solvent, and it's necessary, especially in the formation of these things called dispersions. You'll hear me talk about dispersions, I'm sure, in future episodes. But dispersions are your solutions, are going to be your colloid dispersions, and then you're going to have things like coarse dispersions, if this brings up any memory for you here, like emulsions and stuff. Now, a solution, a solution is when you have a solute such as sugar, salt, that are very small. And what you do is you're mixing that solute, that kind of solid, into the liquid, and they completely dissolve within it. So when I mix salt and water together, the sugar and the water mix perfectly, and the salt, as long as I mix it enough, becomes completely dissolved, correct? It's the same concept of adding honey to hot water or tea, is that sugar completely dissolves throughout it. You don't see just sugar molecules throughout. Your honey mostly just dissolves within there, correct? Colloids are your second type that you need to be familiar, and colloids have several like sub dispersions here. So colloids are different because unlike solutions, colloids never truly dissolve into the larger due to their larger size. So they really never dissolve, colloids do. And there's a few different types of these colloids. One is your emulsions. You know emulsions, which is when you're mixing a liquid to a liquid, like when we mix oil and water together to make a vinaigrette, right? Emulsions do not completely dissolve within each other, but they may become dispersed together. You mix those up, you still see the little fat molecules within the water, right? They don't completely dissolve, but they just become a little bit broken up. Gels are also an emulsion. They're a liquid in a solid dispersion, such as making jams, gelatin, cheese, or butter. When I'm putting liquid into a solid, this is also going to be a gel or a type of dispersion there. In foam is a third type here. It's a colloidal dispersion of a gas in a liquid, such as doing whipped egg whites in a meringue or making marshmallows. There is gas trapped within this that we see, right, within these different formations. These dispersions that are kind of eventually, can mix and change, right? The third type we would need to know is known as coarse dispersions, and coarse dispersions truly never really dissolve, they more settle. Cornstarch is a really good example of this type of dispersion, of this coarse dispersion, because you mix the cornstarch within, it never really truly dissolves. It's just kind of floating within the water and then it can settle out, right? So that's kind of a good example of that too. Let's finish with some more chemical properties for this topic before we dive into some PQ. The pH of water is largely neutral, not acidic nor alkalytic. It helps our body to stay nice and neutral overall or close to neutral. Hydrolysis is a super important RD exam term that I need you to know because hydrolysis is the chemical reaction in which water is breaking bonds from larger molecules into smaller molecules. And it does this all throughout our body in digestion, it does it all throughout the process of the body. So it's a big key one. What hydrolysis does is the formation or the addition of water can break these bonds. A lot of these bonds that help to keep these large molecules together, the hydrolysis is what comes in to break those. So if I have like a large sucrose molecule, right, I have this disaccharide. What hydrolysis does is when I need to absorb sucrose or the monosaccharides of sucrose, the water comes in and breaks those bonds, right? So it breaks the sucrose to become glucose and fructose, so then it can be used in any way that I would like it to be. So that's just a way that hydrolysis does this, and it does it all throughout the body, several times through digestion. It's very important through there too. Osmosis is just another key one that I need you to know. It's very important to the whole body as just an overall topic. It's the concept of water moving from an area of low concentration to high concentration. And when we say concentration, we are saying concentration of a solute, okay? Let's use a saltwater example. We have kind of this bath, and in the middle is a barrier. On one side of the bath is just regular tap water, and on the other side of the bath is going to be salt water. Very, very, very salty water. Well, between that membrane, what water loves is it loves equilibrium. It loves balance here, folks. So if on one side of my bath I just have tap water and the other side is salt water, the water wants to balance this out. So the water will follow from the tap water tank to the saltwater tank, because in the saltwater tank is where all of that solute is, all of that salt is. So it follows into that other tank so that it can reach a balance and equilibrium between both sides. We see this in food and we see this in the body. In the body, when you eat lots and lots of salt, or if people chronically eat lots of salt, we know it causes high blood pressure, right? You have more salt in your blood, and thus more water follows into your blood, which makes your blood pressure higher. This is osmosis to me. We have higher amounts of solute, the water follows the solute, the blood pressure goes up. Seems to make sense to me. We see it in food all the time too. When we have peppers, I have some peppers right now that I want to process, and the peppers themselves, they have a lot of water within them. I'm going to put them in a dehydrator, and the dehydrator is going to make the outside air very, very hot and very, very dry. So the water says, hey, through osmosis, I want to follow from the low concentration to the high. It says it dissipates and it dissolves out of my peppers because it's trying to balance out that equilibrium, right? Thus, that's what makes my peppers dry and helps them to stay fresh for a long time. One last topic today, before we do PQ, is water activity, a concept that I think is very understandable once we get it down. Water activity is a scale we use to measure the amount of free versus bound water in a food. The scale goes from 1.0, high water, to zero point 0, or no water. Foods that are high in water content or water activity are things like milk, poultry, fruits, vegetables, and some of those ready to eat foods. Foods that have low water activity would be things like dried grains, flours, beans, and rice. Why does this matter? Well, the water activity is necessary to know because bacteria needs and loves water to grow. Remember our fat Tom here. Bacteria loves water. And bacteria needs a water activity of, note this, about 0.85 to 1.0 or above. Okay, let me reiterate that. So 0.85 to above or 0.85 to 1.0, that is the area where bacteria love to optimally grow. So that's why you see those high water foods like milk, like yogurts, like meats. That's why they spoil so quickly. When we dehydrate foods, you're removing a lot of that water activity from things, and that's what increases the shelf life of your foods is by removing the water of them. So 0.85 to 1.0, that's going to be that prime time for bacteria there. Let's apply these to some PQs here together. What is the process by which water splits a large molecule into several smaller molecules? A, B, C, or D? A is osmosis, B is heat of vaporization, C is fission, and D is hydrolysis. What is the process by which water splits a larger molecule into several smaller molecules? As we approach these, we have to use our process of elimination here, folks, or PO. So I'm going to write A, B, C, and D next to each answer. As I go through each, I'm going to see whether I think it's a good answer, a bad answer, or questionable. If it's a bad answer, I'm not going to consider it. I'm only going to focus on the answers that are saved and I can focus on here. So for A, osmosis. I am going to get rid of osmosis because I don't think osmosis will be the process of splitting bonds or molecules. It's going to be the process by which water moves from that low solute concentration to the high solute concentration. Answer A is out for me, folks. B, heat of vaporization. I'll put a question mark by this. I don't think it's going to be a good answer, but I'm just a little questionable at the moment and I want to come back to it. C, fission. I don't remember talking about fission today in this lesson. I'm just going to cross out fission. I don't think it's a good answer, and it's not a term I'm familiar with. Or D, hydrolysis. Okay, my answers I have left over was B, heat of vaporization, or D, hydrolysis. What is the process by which water splits a larger molecule into several small molecules? That is going to be D, hydrolysis, as my best answer. Do you see how I got rid of the answers that I knew weren't good fits and I only was able to focus on the ones I knew that were left? This is putting me in the best position to get this question right, and that's what we need for exam day. Let's try number 2. Foods at higher altitudes will cook blank due to the blank atmospheric pressure. Okay, let's see our answers here. My answers are A, slower, increased, B, faster, decreased, C, faster, increased, or D, slower, decreased. Okay, for these kind of 2-answer ones, what I'll normally do is I'll take the question and I'll plug in each answer to determine if I think it's a good one, bad one, or questionable. So foods at higher altitudes will cook blank due to the blank atmospheric pressure. Let's see. Starting with answer A, I'm going to read it with answer A inserted. Foods at higher altitudes will cook slower due to the increased atmospheric pressure. Okay. Well, I know that higher altitudes will cook food slower because that boiling point is lower. I don't know yet about the atmospheric pressure. I feel like it's going to be decreased atmospheric pressure, but I want to just put a question mark by A for right now, just a question mark. For B, foods at higher altitudes will cook faster due to decreased atmospheric pressure. I am going to get rid of B because I knew the foods are not going to cook faster. They're going to cook slower because I know that at higher altitudes my boiling point is lower. So I'm cooking them at a lower temperature. B is out for me here, folks. For C, foods at higher altitudes will cook faster due to the increased atmospheric pressure. Okay, I'm going to rule this one out as well because I'm not looking for ones where the food is going to cook faster. I'm going to go to the ones that cook the food slower. So B and C are out for me. D, foods at higher altitudes will cook slower due to the decreased atmospheric pressure. I like answer D. It fits with the foods cooking slower, and I know that it's going to be better for this atmospheric pressure. If I'm stuck between A and D, I'm going to go with D as my best answer, that foods at higher altitudes will cook slower due to the decreased atmospheric pressure. Good work, everyone. One more question here for us to go through. Bacteria will grow best at a water activity of A, 0.7 to 0.9, B, 0.85 to 1.0, C, zero point 0.5 to 1.0, or D, zero point 0.8 to 0.95. Bacteria will grow best at a water activity of A, B, C, or D. All right, I'm going to write A, B, C, D next to each answer and let's see what we like. For A, 0.7 to 0.9. It seems close to the answers that I wanted. I didn't think zero point 0.7 was quite the number I was looking for. And why wouldn't it just go all the way up to like the highest amount, right? I would actually rule out A. It just feels like a funky answer to me and not the numbers I'm looking for. For B, 0.85 to 1.0. I like this one. I felt like that 0.85 was a good triggering number when it came to water activity, and it fits that it would go all the way up to 1.0. Why would it stop at 0.96 or something? So I feel like B is a great answer. I'm going to hold on to that one. C, zero point 0.5 to 1.0. This zero point 0.5 feels much too low for growth of bacteria. Foods at this low will definitely not be growing bacteria. So I don't think this would be a good fit, and I'm going to rule out A as well as C in this case. And then D, zero point 0.8 to 0.95. It seems pretty close to what I want. So right now I'm between B and D. B was 0.85 to 1.0, which I really liked, or D, 0.8 to 0.95, which I was questionable on. In this case, I need to go with my best answer, which is the right answer, which is that bacteria will grow at a water activity of 0.85 to 1.0. That's the area that it really, really loves for that. That's a wrap up for today's lesson, RDs to be. I hope you listened, you learned, and you enjoyed having this short little lesson together on today's podcast. Remember that passing this exam is a journey. We all need assistance along the way. Do yourself and me a favor. Hit the subscribe button if you haven't. Tell other studying students, rate, review, and just help spread the word. And remember, as always, happy studying, RD to be.